Hello, welcome to Maths with EJD. In this video, I'll be solving a structured problem on rank correlation and errors. Okay, so find the rank correlation coefficient of the preferences for Coke and Fanta by the junior staff in the bursary unit of a university as shown in the table below. So of course, X will represent Coke, while Y would represent Fanta, I want to believe. And then you have all the data 9, 7, 10, 8, 4, 5, 1, 11, 7, 12, 12, 17, 15, 9, 13, 10, and 6, 3. And then you have to discuss decision rule and expatiate on type 1 and type 2 errors in statistical analysis. So let's go for it. As usual, the first part is want to find the rank correlation, rank correlation coefficient. So once you hear rank, that's more like it's non-parametric correlation type. So the first thing you want to also write is the formula. So RS is 1 minus 6 summation of D squared divided by N into N squared minus 1. So two key things here. You have D, that is actually the difference between the ranks for each pair. Difference between ranks for each pair. So that's going to be explained in jiffy. So 9, 7 is a pair, for instance. If by the time you finish ranking them, you get the ranks and then you now find the difference, that's your D. Then that will be squared later. Then actually N is the number of pairs you have. So N is the number of observations or pairs, number of observations or pairs. So here that's like 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 pairs there. All right, so with that explained, we can go ahead and do the table. So let's first of all start with the pairs. We have X, Y, and they are 9, 7, 9, 7, 10, 8, 4, 5, 1, 11, 7, 12, 12, 17, 15, 9, 13, 10, and 6, 3. 13, 10, and 6, 3. Like that. So you have to be sure it's right. 9, 7, 10, 8, 4, 5, 1, 11, 7, 12, 12, 17, 15, 9, 13, 10, and 6, 3. Okay, so we are good to go. The next thing we have to do is to rank them. So we can say this can be rank of X. Okay, since the data is different now, so we can go rank of X. Then we have rank of Y. And when it comes to ranking, right, we have to look at the position each one occupies, starting from the list. So for X, the smallest value for X is 1. So it comes first. Then the next one is 4. So 4 will be number 2 in rank. And then after 4 is 6, which is number 3 in rank. After 6, we have 7, and 7 is number 4 in rank. 7 is number 4 in rank. After 7, we have 9. 9 is 9 is number 5 in rank. Then after 9, we have 10. 10 is number 6 in rank. And then we have 12. 12 will be number 7 in rank. 13 will be number 8 in rank. Then 15 is number 9 in rank. Of course, they're 9 in total. Then we talk about the rank for Y. So the smallest value for Y is actually 3. So this 3 is number 1 in rank. Then after 3, we have 5. So 5 is number 2 in rank. 5 is number 2 in rank for Y. And then we have 8 is next. Is it 8? Yeah. Uh 8, will it be 8 now? 7. 7 is number 3 in rank. Then 8 is number 4 in rank. Then 9 is number 5 in rank. 9 is number 5 in rank. Then 10 is number 6. 10 is number 6. 11 is number 7. 12 is number 8. And 17 is number 9. Normal, I mean, in this case, we don't have a case of same number. Like maybe you have three in two places. So instead of just assigning, if you had two threes, for instance, that'll be first and second. So it means you have to add the ranks 1 and 1 plus 2 divided by 2. So each three will now carry 1.5, 1.5, but we don't have that in this case. So because all the numbers are unique. So we have found the ranks, right? And don't forget, this is about rank correlation coefficient, and it's or otherwise known as Spearman's rank correlation coefficient. So now we have found the rank, so we can go ahead and do and find the d and d squared, which we need. So from what we have here, we need n, we need d, basically. So let's go for d. So now we have we need d and d squared. So we need d squared. D is simply the difference between the ranks. So this will be for this 5 minus 3, that is 2. 6 minus 4 is another 2. 2 minus 2 is 0. 1 minus 7 is minus 6. 4 minus 8 is minus 4. 7 minus 9 is minus 2. 9 minus 5 is 4. 8 minus 6 is 2. 3 minus 2, 3 minus 1 is 2. Then to square this one, 4 raised to power 4 is, 2 squared. 2 times 2 is 2, is 4. 2 times 2 again is 4. 0 times 0 is 0. Minus 6 times minus 6. Minus 6 times minus 6. That's minus times minus plus 6 times 6, 36. So this is 36. Then minus 4 times minus 4, that's 16. Minus 2 times minus 2, that's 4. This is 16 again. This is 4. And this is also 4. So in all, we need the summation of all the square of d. So this would be 4 plus 4, 16. 4 plus 4, 8. 8 plus 36 is 44. 44 plus 16 is 60. Yeah? 64. 64 plus 16 again. That is 80. 80 plus 4, 84 plus 4. That's 88. And of course, we already know that n is equal to, 1, 2, 3, 4, 5, 6, 7, 8, 9 pairs. So n is 9. So with that done, we can go back and say and compute the rank correlation coefficient. So we have Rs, which is equal to 1 minus 6 summation d squared all over n into n squared minus 1. So we can slot in the values. So we have Rs equals 1 minus 6 times 88 divided by 9 into 9 squared minus 1. Okay. And then that would be Rs equals 1 minus, let's do 6 times 88. Before we do all that, right, we have 6 times 88 divided by 6 into 9 squared is 81 minus 1. So we have Rs to be equal to 1 minus 6 times 88 divided by 6 times 80. 6 times 80. And then RS would be equal to um, RS. Okay. So we have 6 times 88 now. 6 times 88. That's 528. That's 1 minus 5, 28 divided by 6 times 80. That should be 6 times 80. That should be 480. 480. Okay. And with that now, we have RS. RS is equal to 1 minus 528. 528 divided by 480. 528 divided by 480. That will be 1.1. This is 1.1. Okay. So we are going to get a negative value the way it's coming. So yeah, 6 times 88 is 528. 9 times 80. Oh yeah, I was really wondering that something was not going well. Yeah, sorry. N is, yeah, I was wondering why this happened. Thank God. So this is 9 here. I was really hesitant to proceed. This is 9. So 9 times 80 is 720 for sure. Yeah. Now I'm happy because I was already wondering why that was going to be negative. But it can actually be negative, right? But let it really be negative, not because of any error. So this is 528 divided by 720. 720. So that is 0 point. That is 0 point 0 point. So at this point it becomes like an approximation. 1 minus 0 0.77. Let's do it to four decimal places. 7333. So finally, RS is approximately 1 minus 0 0.7333. 0.7333. And then we have that to be approximately 0.2667. So this is the rank correlation coefficient. Okay. Can say therefore the rank coefficient the rank correlation coefficient for Coke and Fanta, I believe, because we're given Coke and Fanta, Coke is X and Fanta is Y most likely. For Coke X and Fanta Y, it's about preference. The rank correlation coefficient for Coke and Fanta preference is 0.2667, which is a weak, it's a weak positive correlation. So the effects are not that strong. Basically, that's what that implies. So that goes, and then we can go to the B part and deal with that. Okay, so let's go to the B part where we have to now talk about decision rule and all that. Let's go for it. So B now, decision, we are talking about the question is asked, we are told to discuss decision rule and expatiate on type 1 and type 2 errors in statistical analysis. So let's start with decision rule. Decision rule. So in hypothesis testing, in hypothesis testing, A decision rule is a criterion used to decide whether to reject the null hypothesis So it is based on the significance level alpha, which represents the probability of rejecting the null hypothesis when it is actually true. Okay. Um, if the test statistic, if statistic, the test statistic is usually something you will compute. If the test statistic falls into the critical region, into the critical region. So you compute the test statistic, but you get the critical region from a distribution table relevant to the kind of test you're carrying out. So if the test statistic falls into the critical region, that is the critical value, beyond the critical value determined by alpha, determined by alpha, the null hypothesis is rejected. The null hypothesis is rejected. Generally speaking, if the test statistic is greater than the critical value, then you reject the null hypothesis. But if the test statistic is less than the critical value obtained from a table, then you can fail to reject the null hypothesis, or you accept the null hypothesis as it were. So the null hypothesis is rejected if the test statistic falls into the critical region. That is, it goes beyond the critical value determined by alpha. So that is about decision rule. So let's talk about type 1 and type 2 errors. How does the question go? So it's always nice to answer the question based on the way it's asked. Expatiate on type 1 and type 2 errors in statistical analysis. Okay. So we talk about type 1 and type 2 errors now. So here, first, let's go for type 1 error. Type 1 error, which is also known as false positive. False positive. Okay. So type 1 error actually occurs when the null hypothesis, is true. The null hypothesis is true, but we incorrectly reject it. So type 1 error is rejecting the right. Type 2 error is accepting the wrong, something like that. So type 1 occurs when the null hypothesis is true, but we incorrectly reject it. So the probability of a type 1 error is denoted by alpha, which is also known as the significance level. I mean, the most common significance levels used is 0.05 or 5%. 1% is also used. So the higher the accuracy, the lower the significance level should be. So that's about type 1 error. Now let's talk about type 2 error. Type 2 error, which is false negative. That is accepting the wrong. So in this case, type 2 error happens. It happens when the null hypothesis is false, when the null hypothesis is false, but we fail to reject it. That is, we accept it. We fail to reject it. Okay. So the probability of a type 2 error is denoted by beta. It is inversely, it is inversely related to the power, to the power of the test. Inversely related to the power of the test, which is 1 minus beta, which measures the test's ability, the test's ability to correctly reject a false null hypothesis. Okay. Now, to put everything together in practice, right? In practice, minimizing minimizing both types, minimizing both types of errors is crucial. But there is a trade-off. There is a trade-off between them. And then, just like I said before, a lower significance level, a lower significance level reduces the likelihood, reduces the likelihood of a type 1 error, but may increase the risk of a type 2 error. So if you have a very low significance level, like 1% or 0.01, that means that there's a chance of there's a 1% chance of making the wrong decision, basically. So if you make it very small, so you can easily reject a true null hypothesis, you know. So it will increase, I mean, it will increase your chance. It will reduce your chance of rejecting a true null hypothesis, but it will increase your chance of accepting a wrong null hypothesis. That's the idea. Okay, so that brings us to the end of this particular question. If you have not subscribed to this channel, be sure to do that. Hit the notification bell also, so you can always get notified each time a new video is released. Don't forget to comment. Tell me if you want to answer a question or treat a particular topic, and I can find time to do that along the line. And don't forget to like and share so that more people can have access to this learning. Till I see you again, have a nice time. Bye.